Alrighty, let me at least start with introductions. So today we have two student presentations. Alireza will go first and Lohit will go after that. Now that Ari is here, we can actually get properly started. So both of our student presenters today are second-year PhD students in ECE. Their topics of research are slightly different. Alireza is doing research on the software and system security front, and Lohit is doing work on privacy-preserving technologies. Did that capture it somewhat? Yeah. At least what I inferred from the title of your presentation. Alireza is my advisee. Lohit is Ajay Josh's advisee. So we'll be security heavy today. With all that said, Alireza, go away.
So thanks for the introduction. So today I'll be presenting user-IT comprehensive code signing to prevent IT device manipulation, and also this work has been accepted to Architect 2025, and I'll be presenting it there next month. So I'm pretty sure everyone in this room has used an IT device at some point, maybe a router, or a smart camera, or even smart speaker, you name it. And but let me first give a definition for Internet of the Things or IoT devices. So an IoT device is a network-connected embedded system designed to perform a specific, narrowly defined task, often with minimal user interaction. So for the rest of this talk, when I say IoT devices, I specifically mean Linux-based IoT devices, those running some versions of the Linux kernel. So IoT devices are everywhere, they're prolific, and in fact, their global number has already surpassed the human population and is still going rapidly. But despite being so prolific, they remain deeply insecure. So there are hundreds or even thousands of CVEs assigned to different IT devices and their components by now. And also weak or hard-coded passwords remain the leading cause of compromise for these devices. So these vulnerabilities wouldn't be as concerning if, or insecurity wouldn't be as concerning if they're only affected individual devices. But in reality, they are exploited at scale to build massive botnets, impacting not just the device owners, but countless others who had nothing to do with these systems. So this is a direct quote from Bitdefender guys that prove what I just said. That they're mentioning that compromised IoT devices serve a darker purpose as being weaponized in botnet attacks. So with that being said, let's see what is IoT device or specifically what is a bot. So as its name suggests, a botnet is a large network of compromised IoT devices that are remotely controlled by an attacker and used to send a huge traffic to the victim side to perform a distributed denial service or DDoS. So one of the most famous examples was the Mirai botnet back in 2016, which infected hundreds of thousands of IT devices and caused a massive internet outage worldwide by taking down a DNS provider named FHE.We. But botnets aren't the only way attackers can make profit from compromised IT devices. And with the rise of cryptocurrencies, attackers increasingly use these devices to mine crypto at a scale, exploiting their always-on nature and large deployments. So generally speaking, to weaponize an IoT device, attackers first need to compromise the device and then download their malware and then execute it to fulfill their malicious intent. So in this work, we focus on breaking this chain at the final step, which is execution of the malware, by preventing any unknown code from running and thereby stopping IT device weaponization. So to address this risk, recent works have introduced a range of host-based defense mechanisms for IT devices designed to enforce code integrity to prevent unauthorized actions. So for example, Hades IT works in two different phases. First, in profiling mode, Hades monitors and collects information about all calls to execute system call and generate the whitelist accordingly. So simply they run a Hades IT in a profiling mode or recording mode, and then they need someone to work with the IT device to learn all the legit behaviors of the device, and then they use this whitelist in a protection phase to and enforce this, allow this on each invocation of execute system call, and thereby they protect the device from unauthorized actions. But there are some shortcomings on this work. So first is relying on profiling mode. Even though IoT devices are built for specific tasks, it's unrealistic to assume we can fully learn all their possible behaviors during profiling. So the real challenge here is that some legitimate actions may be missed, and if those are wrongly flagged as malicious, it could disrupt the device's normal operation and even break the overall system. Also, they only care about execute system call integrity, so meaning that the tensor blind eye on shared libraries or script interpreter execution. So attackers can use these two attack vectors of execution to bypass any protection proposed by HEDIS. Also, it faces limited scalability because it must be recompiled as a kernel module for each individual device, which requires a manual extraction of configuration options. And also, in some cases, they need to recompile the whole kernel for to be able to properly load the kernel module into the targeted device.
This also allows you to attack using whitelisted program.
Yes, you can use you can do code reuse.
Yeah, code reuse still.
So after looking at Hades IoT, we saw that while it does a good job checking direct execution of native binaries, it doesn't capture other types of execution. So attackers often get more creative. For example, in the middle, we have two ways of using dynamic linker to bypass protection proposed by Hades IoT. So here, the first, attackers can execute a linker directly to run a program. Or the second one, they can use LD preload environment variable to inject a malicious shared library into a legitimate process. So in both cases, execute system call, or the first argument of the execute system call will be passed to a whitelisted program. So Hades IoT won't prevent any of these two executions. Also, the script interpreter execution can bypass those protections. For example, an attacker can rewrite, attackers can rewrite the malicious software completely into, let's say, a Lua script, and then just run that script through the interpreter. Or they don't need to completely rewrite their malicious software, or they can use a process hollowing technique, which spawn they need to write a loader to spawn a legitimate process, a whitelisted process. And then using a ptrace system call, they can rewrite the memory of that process. So they execute malicious software inside a shell of a whitelisted process. So these are remaining execution paths that need to be addressed. So now let's have all the remaining challenges in one place. So profiling, so relying on profiling, and profiling means benign behaviors causing false alarms and disrupting device functionality, so you cannot rely on that. And also, process level granularity is insufficient, so interpreters need finer grain integrity. But before I explain how we address these challenges, it's important to first understand what kind of attacker we are actually defending against, or in other words, our threat model. So in threat model, we assume that attacker has already compromised the IT devices, whether it be by a vulnerability or default credential brute forcing. And also, we assume that attacker has root privilege because most IT devices expose only a root account, and also their goal is to weaponize the device to join botnets or mine cryptocurrency or deploy any kind of malware. We also made some assumptions about the system under our protection. First is that the IT device need to have a secure boot enabled. Also, we assume that a clean firmware contains no built-in crypto miner or DDoS client or any other kind of map.
Do you assume, what do you assume is in the firmware? Where does the operating system reside?
By the firmware.
Firmware? Yes, that's another assumption. You could run the operating system as software, right?
I mean, the firmware image.
In other words, if I have root, what can I do? Can I change default programs? Can I, usually with root on like a Linux system, you can do whatever you want, everything.
Yes, that's true.
Right?
But I mean, I don't understand this term. What do you mean the operating system is inside?
Well, I can take ls and change the executable to do anything I want. And since it's whitelisted,
So no, it's not. It's not like you whitelist the only path to the program. You compute the hash of the program, and that's inside the whitelist. So
I can change the whitelist.
So yes, that's true.
right.
You can change the whitelist.
I'm trying to understand what is having root.
So there are some protection over the whitelist, which I'll explain later. But yes.
But you make no assumptions about the safety of anything. In other words,
I mean, we have a trust. We have a chain of trust, which I will explain later. It will show that how secure boot as a root of trust will enable us to protect the whitelist and other components.
all right, I'll wait and see.
So here comes the key insight. As I've already mentioned 2 times, IT devices are general purposes machines. They have a fixed purpose and static software stack. They're built to do one thing, and they almost never change after deployment. So just ask yourself, when was the last time you installed software on your home route? So the approach we took is because the software set remains constantly statically generate and allow this build time to address the first challenge and use it for runtime integrity verification. We also extend this verification into the interpreter environments to cover a script-based execution, and here will be address second challenge. So now I introduce UCIT's 3-stage approach, which is a lightweight execution control mechanism designed for IT devices. We built the prototype, our prototype on top of OpenWRT, a widely used aftermarket IT operating system. So this overview figure has 2 more details. So let me abstract each stage. So the first stage, which happens once per firmware build, generate the allow list and apply patches to the firmware. The second stage, which happens once per device boot, verify the allow list integrity at boot and load it into kernel memory. And the stage 3, which occurs continuously throughout the device lifetime, enforces the allow list for each execution request and blocks any unknown execution along that path. So for the first stage, UCIT modifies OpenWRT source build pipeline to enable integrity measurement and enforcement by inserting hooks into core components such as execute system call, FHE module system call, write, unleak, and other interpreters inside the firmware. And then it generates a static allow list for computing a SHA-256 hash for each file in the firmware image. And also, it also protects the allow list from tampering by signing the allow list with a private key and store the corresponding public key in the kernel key. So the output of this stage would be a patched firmware image with built-in integrity measurement capability and a statically generated allow list. So for the second stage, which is a boot time initialization, UCIT verifies the integrity of the allow list and load it into kernel memory, or in more detailed steps, the UCIT kernel module run after file systems get mounted, and it verifies the allow list signature using the embedded public key from the last stage, and then it loads the verified hashes into a kernel space in memory hash table, and also create a character device with octal interface for user space interaction. So the output of the second stage would be allow list and loaded in kernel memory and ready to be queried by kernel or user space hooks.
I'm going back to my earlier question. So if I'm root, can't I modify kernel memory?
Or you need to insert a kernel module, but you cannot do that.
Okay, so you're assuming that all kernel code is locked at boot.
I mean, you can insert the kernel modules at runtime, but only those kernel modules that are from the firmware image originally. You cannot insert any arbitrary kernel module.
And who checks that?
The hooks inside the FHECore module system call, which the next slide. So for
you said I have root. Why can't I just replace the kernel image that's on the firmware?
I mean, you can replace the kernel module on the firmware, but then the hash would be changed and the allow list, the hash wouldn't be in the allow list. So
No, I mean the kernel image itself, not the module.
the whole kernel,
Yeah.
like flash a new kernel, well, then the secure boot will stop you.
Okay, sorry. You hadn't mentioned secure boot, so I was wondering how you were doing the verification there.
So for the third phase, which is the runtime enforcement, so in this stage, stage 3 focuses on enforcing the allow list in runtime across execution path, blocking unauthorized code execution using hooks inserted in first stage. So we divided hooks into 3 groups: self-defense hooks, native execution hooks, and interpreter execution hooks. So first, let's talk about how ZSIT protects itself before protecting anything else. So at the left side, we have write and unlink system calls. We inserted some hooks into these 2 system calls to block modifications to the allow list and the character device. So the purpose is to prevent attackers from injecting hashes or removing them, which could cause a dot in the latter case. And also we inserted some hooks in a hook into FHECore module system call to allow only allow listed kernel modules to be loaded. The purpose here is to ensure attackers cannot hook into ZSIT or remove or override its in kernel allow list.
How do you know if you're writing to the allow list? How do you check that?
Just a path to the allow list.
So if I use a symbolic link, you won't notice it.
Symbolic links happens before the write system call. So the write system call will take that.
You know it's specific.
Right.
You're looking at the inode that's being written to.
One more question about kexec. Why can't I just put a kernel on there that doesn't enforce these and then kexec to it if I have root? You could do that from
I can understand. Can you?
I can. What's stopping me from kexecing to an unprotected kernel?
So what is kexec?
Kexec is the ability to change kernels without rebooting, right? You can load a kernel image into memory and then you call kexec and now you're in the new kernel without having to power cycle.
Well, I didn't know about that, but
There are ways to disable it. You should consider making sure that it is disabled for your.
yeah, thanks. So for the next group of hooks, we have native execution hooks. Starting with FHECore hook, we insert a hook into FHECore system call to allow listed native code to run. And the purpose is to prevent attackers from launching unknown or malicious code through direct execution. And also into a dynamic linker, so to only allow listed shared libraries and native code to run, to preventing attackers from using the dynamic linker as an ELF interpreter to bypass exit-v hook or inject malicious library into allow listed program. So ZSIT can capture or can block all these 2 ways of, or other ways of using dynamic linker to execute on the code. So for the last group of hooks, we have interpreter level execution hooks, starting with Lua interpreter, because just Lua interpreter is the default interpreter inside OpenWRT. We also did the same for pipeline interpreter. And we inserted hook into Lua interpreter to allow listed Lua scripts to run. Also, we block the inline or CDN execution. And the purpose is to prevent attackers from using the Lua interpreter to bypass native code execution. And also the shell interpreter too. But here we could only allow we could we insert a hook to only allow listed shell scripts to run. There is a limitation for shell interpreter because we cannot block inline shell execution without breaking some of the WRT functionality. For example, the right side, you can see a very same command that Open Derivative web interface uses for changing user passwords. And also, so the best practice here would be to use a restricted shell to not to prevent attackers from using some special characters. But so here it would break some openWRT functionality. So we left it as a feature. So now let's talk about trust chain architecture inside useIT. But before that, what is a chain of trust? The chain of trust is a security model that ensures each component of a system is verified before it is trusted. So here at the very bottom level, we have scripts and shared libraries, which get verified at runtime by user space hooks. And then the user space hooks alongside with other binaries and kernel modules would be verified at runtime by kernel space hooks. And then the kernel space hooks or kernel integrity would be verified at boot time by the secure boot, and the secure boot would be root of trust. So we evaluated useIT prototype implementation on OpenWRT version 24 in both simulation environment and hardware environments. We used a data set of more than 81,000 real ARM-based IoT malware samples from famous malware families like Mirai. And we tried to answer this research question. First question is, can the useIT prevent execution of real IoT malware? And how does each hook contribute to runtime integrity? And also, what is the runtime overhead introduced by useIT on CPU usage and memory usage? And the final question is about functionality, which does useIT affect the core functionality of an IoT device such as router? So as for the first question and the second one, useIT prevented 100% of 81,000 real ARM-based IoT malware samples, obviously because none of those samples hashes live in the allow list. And also we compared useIT with useIT and also ESPion previous works in terms of some execution features. As you can see in the first row, useIT and the other one relying on profiling mode, which the useIT does not, and create a allow list by statically at real time. Also, both of the previous works can cover native code execution and kernel module loading, but they lack coverage on dynamic linker code loading and interpreter-based code execution, which is not the case for useIT. And for the last one, shell script execution, useIT do it partially, but we observed no real world malware purely written in shell script, and all observed malicious scripts served as droppers for other ELF payloads, which were blocked eventually by the exec-v and the dynamic linker hooks eventually. So for the runtime performance evaluation, we execute a shell script periodically once per second to execute 4 other programs: static ELF, a dynamic ELF, a shell script, and load script. They simply just print a hello world, and then to track the usage of CPU and memory via ZAR over 5, 15, 20-minute interval. And we repeated each 10 times to reduce the randomness. As you can see in the table, useIT introduced 33% overhead on the CPU, but we argued that so this workload does not reflect typical IoT behavior, and real devices rarely respond processes this frequently. So we did this phase-wise timing measurement inside QEMU emulation, and we simulated the OpenWRT instance as a router in the QEMU, and these are the measurements. Because in a steady state, we observed no invocation of ubiquity checks, which prove the real devices rarely spawn processes this frequently, and means that the ubiquity, the overhead introduced by ubiquity is negligible in real world operation.
Question.
After telling you have 4 more minutes.
Oh, okay.
Yeah, the last slide. So for the last question, we have, does ubiquity introduce any impact on the core functionality of a router? So we evaluated this on a real router and QEMU emulation. So we observed 0.1% overhead on QEMU emulation and 0.8% overhead on the real hardware. But this overhead is not a noticeable overhead because it was just inside the measurement error. So in summary, first, IoT devices have a specific and fixed function, unlike general purpose systems, and then this insight allowed us to use a statically generated alias, and then ubiquity extended the integrity enforcement into interpreters, environments, and the loader addressing a gap in previous works. And also we evaluated ubiquity on 81,000 real-world malware samples showing 100% prevention and tested on real hardware with no impact on core functionality. The code is online and the artifact have been evaluated, and that's it.
We have time for a few quick questions.
But I have another one. So can I not just trivially bypass this by overflowing the call pointer instead of going to the beginning of, let's say, exactly skipping your checks? In other words, you patching things like exactly and what have you so that it does some checks, right?
Yes.
But can't I just skip those checks since I have full control over the...
I mean, how do you want to, how do you want to escape those checks? That's the question, right?
Jump to somewhere inside the procedure after you've done your checks.
So basically you need to execute your code, right, to do that. So before, you cannot execute any unknown code. How do you want to jump to it?
Oh, I see. All code is locked down. All code is under firmware. I mean, I'd have to do it through a script, right? I could have a script that explodes some sort of overflow or something, overwrites a pointer.
Oh, you mean the memory corruption?
Yeah.
So basically, ubiquity does not prevent memory corruptions, but it raises the bar high enough for attackers, so make it so hard for attackers that cannot exploit it. So you need to use a complete shell code inside the program because you cannot jump or you cannot run any new process. So you have to execute all your shell code inside that.
Right.
Inside that memory layout. But yes,
okay.
If you have
so that's out of scope, you're saying, for the defense.
Yeah.
Okay. Very much.
Other questions? So while Lohit is set up, let me ask a question. This sounds very, very similar to the IMA subsystem that the Linux kernel already supports, right? Integrity measurement, it's already in the kernel. It has been there for over a decade. It's used by real-world systems, but
IMA or integrity measurement architecture does not prevent any scripting execution, and if you want to add those checks inside interpreter level execution, this would this would be the same as this ubiquity.
So good afternoon, everyone. I'm Lohit, and I'll be presenting our work FHECore, Rethinking GPU Microarchitecture for Fully Homomorphic Encryption. So here is the outline for my talk. First, I'll go over the basics of fully homomorphic encryption and the computations that need to be accelerated. And then I'll talk about how fully homomorphic encryption is accelerated using GPUs. And finally, I'll talk about our design, FHECore, which is a specialized functional unit that can be integrated within GPUs to accelerate FHE workloads. So what is fully homomorphic encryption? So FHE is a class of algorithms that lets you compute on encrypted data. What that means is the client can encrypt sensitive information like medical diagnostics or financial records before they are sent to an untrusted third party to be processed on. This way, data is kept encrypted not only during transmission and in storage, but also while it is being computed. So there are several FHE schemes out there that allow you to do this, each specializing in specific applications. For the focus of my talk is going to be on the CKKS scheme, as it is the only scheme that among the ones that are shown here that lets you compute on fractional plaintext values. And this property makes it favorable for privacy-preserving machine learning workloads. Values like 6.1 or 9.6. So otherwise, for something like BFE or BGB, they would have to be integers.
Those are effectively
Real numbers, but yeah, so you cannot encrypt something like 6.1 with BFE, but you can do that with CKKS.
Can you just encode it as 6,1?
Yeah, so you don't need to do that with CKKS though. Yeah. In essence, yeah. Do you have?
If you encrypt it like that, oh, but I can just scale everything by your operation will come to. Right, it will depend on the size of the room.
So in essence, you could do that. You could say that my fractional values are going to take another slot in the plain text, but then you'll have additional overheads where you have to process the fractional slot for fractional and exactly.
It's already so complex in carrots.
Yeah. So was that okay? So in essence, all of these FHE schemes derive their security guarantees from an underlying hard problem. For the CKKS scheme, it is the ring learning with errors problem. I will not be going into the details of the RLWE problem. It would suffice for us to know that the plaintext in the RLWE crypto system, the plaintext is a single polynomial whose highest degree is n-1, and the ciphertext is a tuple of two polynomials whose degree is n-1. And all computations all computations happen in a polynomial ring whose coefficients take values from 0 to q-1, and the highest degree is n-1. Here is an example of one such polynomial whose coefficients range from 0 to 256 and highest degree is 3. So before the client can get started with the encryption and decryption steps, it would have to first generate the encryption key. To do that, the client samples three polynomials, A, E, and S, and computes an expression minus a times S plus E, which is the polynomial in the polynomial ring. So the hardness assumption of the RLWE problem is that given a tuple minus A times S plus E and A, it is very hard for an adversary to retrieve the value S. And this is the assumption in which FHE derives its security guarantees. Once the key generation is done, the plaintext will move on to encode its plaintext, which is a vector. And in CKKS, the vector can take values in the complex range as well to an element in the polynomial ring. The encryption step is straightforward, where the client simply adds the encoded polynomial with the encryption key. And this gives a ciphertext, which is a tuple of two polynomials, both of which belong to the same polynomial ring. Yeah.
How do you code a complex number?
So the reason, so I have in this slide I have denoted that the m can take complex values, and the length of the vector is going to be n over 2. What CKKS allows you to do is it allows you to encode a vector of length n into a polynomial. And since now a complex numbers have a real part and an imaginary part, you can exactly, yeah.
But the real numbers, you could do fractions. You can't do reals, can you?
No, you can. So a real number is an integer. Integer has an integral part plus a fractional part. So that's.
The fractional part could be infinite.
Oh no. So okay. It is a terminating fractional. So it's
yeah. It's not a real. It's a computer real.
Exactly. It's a computer real. So the server side. Okay. Next, I'll talk about the server side operations of CKKS. The server-side operations are slightly more different than the client-side operations. In this example, the black font and arrows correspond to plaintext polynomials, and the red font and arrows correspond to ciphertext polynomials. The first type of operation the server can do is the plaintext ciphertext addition and ciphertext addition. These are relatively simple for the server to do because they are just coefficient-wise additions of the polynomials given to it. And the next type of operation is plaintext ciphertext multiplication and ciphertext multiplication. These are more involved for the polynomial for the server because it has to do a series of polynomial products and follow them up with some ciphertext maintenance operations. And then there is in CKKS, yeah.
What about computation that involves things that are neither additions nor multiplications,
Such as by Boolean logic.
for example?
So there are ways for you to do that through CKKS. You approximate the Boolean logic with a polynomial, with a high degree polynomial, and then you can compute that. But CKKS is not specifically meant to do Boolean logic, so there are other schemes that allow you to do that. Are there any other questions? Okay, so ciphertext. So yeah, I was saying the CKKS ciphertext have an inherent noise term to it, and when you start computing on the ciphertext, the noise accumulates and grows to a point beyond which you cannot do further computations, and that is when the server does this procedure called the bootstrapping. Yeah.
So what about division and subtraction?
So
I understand that the subtraction and division could be interpreted with addition and multiplication, but you should be able to find the inverse of a number.
that's right. So for example, 1 over x, you want to compute 1 over x. The way you would do that is express 1 over x as a polynomial approximation. So you would have to do something like a Taylor series approximation and maybe take the most significant terms and then compute those scalings and multiplications in the ciphertext domain.
But in your ciphertext, you have x, right? So how do you go from ciphertext x to ciphertext 1 over x?
No, so if your question is,
he's saying you use a Taylor series approximation.
Taylor series approximation is one of them, but you could use one of these expansions.
So you express 1 over x as some product and sum of x and by powers and multiplication.
Yeah. So now let us see how polynomial products are computed by the server. Yeah,
So,
sure.
When it's having expense, right?
That's correct.
Yeah. So do you do this after every multiplication gate?
No. So the ciphertext has, you can think of it this way, the ciphertext has a multiplicative budget. So you could do something like, say, 10 multiplications, and the 11th multiplication wouldn't be possible because you don't have enough noise budget. So at that point, you would insert a bootstrapping step.
Okay, and this budget is public.
Yes, this budget is public, yeah. Now I'll quickly go over how servers compute the polynomial products. One way to, let's say you have two polynomials, a of x and b of x. One way to compute the product of the two polynomials is to take their coefficients and perform a cyclic convolution on the two coefficients. This would result in a vector of length n, which would correspond to the coefficients of the product polynomial. But the issue with this is the cyclic convolution has a polynomial time complexity and is not scalable for large values of n. An alternate approach to do this is to.
You end up with
It's a cyclic. No, it's a cyclic convolution.
Yeah.
An alternate approach to computing polynomial products is to take the evaluation of the two polynomials in a common set of points and do a pointwise multiplication of the two vectors that you're given. This has a linear time complexity, and the result of this operation is basically the evaluation of the product polynomial. Now let us see how do you arrive at the evaluation representation from the coefficient representation. The naive way to do this is just evaluate the polynomial itself in the points in a given set of points, but that is equivalent to performing this matrix vector multiplication, and you're back with polynomial time complexity. Turns out you can cleverly choose your set of points that satisfy these conditions, and these points are called the roots of unity. You can do what is called the number theoretic transform. which has a recursive formulation and which giving it a total runtime complexity of n log n. The number theoretic transform has a runtime complexity of n log n, but it can also be viewed as a matrix multiplication. But this time, the matrix vector the transformation matrix is a symmetric matrix.
Isn't it just read solid decoding?
So the new matrix, is it?
Yeah, trying to call. Well, not the matrix itself.
I'm not familiar with what Reed-Solomon decoding is, but
That's a Van der Waals matrix.
yeah, that's a Van der Waals matrix. So in practice, the way these large entities are implemented is, so the large entities are, when you want to perform entity on a large vector, they aren't implemented in a single go. The way they are done is the vector is reorganized as a matrix, and then you perform entity on each column of the matrix independently. Then scale the result with an appropriate twiddle factor, transpose the matrix, and then redo the entity on each column again. The result, when read in row major order, will give you the entity of the original vector. Okay, so the key takeaway from this slide was that a large entity can be formulated as multiple small entities, and each entity, in essence, can be viewed as a matrix vector multiplication. So one thing that I haven't spoken about is the values of n and q that guarantee security for the CKKS scheme. Turns out in CKKS, for you to be able to do bootstrapping and have 128-bit secure, your polynomial degree is going to be of the order 2 power 16, and that requires each of those coefficients to be at least over 1,000 bits wide. And the issue with this is in most processors today don't support operations on 1,000-bit wide. So there aren't adders or multipliers that directly operate on 1,000-bit operands. So this is an inefficiency. And the way this is addressed is through the residue number system, which is an application of the Chinese remainder theorem. So let's assume this polynomial shown here is the large polynomial which we want to decompose to smaller coefficients. Since the modulus 15 can be written as a product of 3 times 5, you can represent each coefficient as its residue with respect to 3 and 5. So 7 modulo 3 is 1 and 7 modulo 5 is 2. And similarly, you will have a vector for each coefficient of the polynomial. There are intermediate steps that require you to go from a smaller modulus to a bigger modulus in the CKKS scheme. And to do that in the RNS representation, you need to do what is called the base conversion step. Let's say you are given an initial RNS representation x1 through xk in the basis set q1 through qk, and you would like to transform it to a basis set b1 through bl. The way you would do this is to use x1 through xk and reconstruct the original large value itself, and then decompose it with respect to the new target basis. In practice, this is what is done, except the intermediate mod q is kind of ignored. And now this expression can be viewed as a vector dot product. Now, since the target basis has L residues that you want to compute, the vector dot product can be seen as a matrix vector multiplication. And now the coefficient has n such vectors to transform. And hence the matrix vector multiplication becomes a matrix multiplication. So bootstrapping, logistic regression, ResNet, and BERT-Tiny are the representative workloads for papers that do hardware acceleration for FHE. These profiling breakdowns were done on an A100 GPU. And turns out the number theoretic transform, inverse number theoretic transform, and base conversion step together account for over 70% of the runtime. And all three of them, like we had seen, are some variants of modular linear transformations. Now I'll talk about how FHE is accelerated using GPUs. So a GPU is basically one big chip that has many of these. It is one big chip that is able to perform a single operation on batches of data. And the way it does that is it has many of these small cores called the streaming multiprocessor. And each streaming multiprocessor has a bunch of ALUs that support different operand types. And the more recent generation of GPUs have these things called the tensor cores that accelerate machine learning workloads. Okay. The way GPUs are programmed is through through the CUDA programming framework, there are software libraries written in CUDA that allow you to, there are domain-specific software libraries that are written in CUDA that allow you to build your application. FHELib is one such library that maps server-side CKK's operations to the GPU. So in presence of FHELib, the way privacy-preserving computations happen is the client does the encryption, decryption, encoding, key generation steps locally using the OpenFHE library, which is a popular standard in the FHE space. And the ciphertext is then transferred onto the GPU. Now, FHELib exposes at the very top level, it exposes the CKK's primitives such as ciphertext addition and multiplication, plaintext addition and multiplication, and bootstrapping. In essence, these are composed of internal routines like key switching, mod up, mod down. But at the very core, all of these functions are built on top, are based on a handful of kernels like the number theoretic transform, base conversion, element-wise multiplication, addition, and automorph. And like we had seen a couple of slides back, the entity, INTT, and base conversion together account for 70% of the runtime. So the way a CUDA program is compiled down to the GPUs, so a CUDA program allows you to have finer control over how you want to utilize the GPU's resources. Let's say, and one such configuration is the number of blocks in the CUDA program. If a CUDA program has 8 blocks, a GPU with 2 streaming multiprocessors could execute 2 blocks, can execute 2 blocks at a time, and a GPU with 4 streaming multiprocessors could execute the same program at 4 blocks with 4 blocks at a time. The CUDA program is then compiled to an intermediate representation called the PTX by the compiler, and this is a well-documented representation by NVIDIA and acts as an adapter between the assembly code that is actually executed on the GPUs and the CUDA program developed by the applications. So it isn't unheard of for developers to use PTX to fine-tune their applications. One such example came out earlier this year, where the developers of DeepSeek had used PTX to optimize their implementations and were able to take advantage of NVIDIA's older GPUs to come up with the DeepSeek model. So, and now the PTX is compiled to the machine instructions, which is not publicly documented and varies for every architecture family by NVIDIA. Here is an example of a CUDA fragment that runs on the tensor core. The sections in beige are associated with data movement, where data is taken from the memory to certain fragments of the register that the tensor core can access. And the green step is where the matrix multiplication actually happens on the tensor core. This, when compiled to PTX, reveals finer information such as such as the elements stored in A are done so in row major order and B are done so in column major order. And the matrix multiplication step is done on 8-bit operands, and the accumulator variable is 32 bits wide. This is further lowered to the assembly instructions that are actually issued, decoded, and executed on the streaming multiprocessors of the GPU. Here we see that a single MMA sync PTX intrinsic is compiled into 2 IMA instructions, and this is specific for the Ampere GPU. If you were to use something like V100, this would actually compile to 16 machine instructions instead of just 2. So in essence, once you have your machine instructions and you want to execute that on the GPU, each streaming multiprocessor has to issue those instructions, decode them, and execute them on the GPU. So even though having more number of blocks gives you more parallelism, but when you map them to multiple streaming multiprocessors, you are essentially issuing, decoding, and executing the same instructions over and over again, and this adds a lot to the energy overhead. Yeah.
So for how much comes from data movement? Because the ciphertext are each, right? So how much comes from data movement, memory management, and how much comes from the computational process?
Are you talking about the breakdown that I had shared earlier?
Yeah.
So those are entirely computation. The time it takes for you to store from an external memory to the GPU memory is not accounted for. Yeah.
But I mean, if I want to compare these two, how do they compare?
So
Is it compute bound or memory bound?
it is memory bound. So number theoretic, so the number theoretic transform and base conversion steps aren't memory bound, but the remaining ones are. So it is a memory bound application, but
But
typically
here you're optimizing
the compute region, yeah.
yeah.
So now that we had seen that the number theoretic transform and base conversions can be formulated as linear transformation, there have been works that look into repurposing the tensor cores to do this linear transformation. And the way that is done is you take your original large vector, do the 4-step NTT process where you perform entity on the columns, then a transpose scaling operation, and then entity on the columns again. And this can, when your original vector is as long as 2 raised to the 16, you can go one level deeper and make each of those inner entities and break each of those inner entities as another 4-step entity. This way, you have a series of operations that are to be done on the tensor core, and then the transpose and scaling operations that would be taken care on the CUDA core. The problem with this is that tensor cores do not support 32-bit wide operands, and for integer they support only 8-bit wide operands. So you're essentially fragmenting each entry of the matrix into 4 matrices, into chunks of 8-bit operands. So you're adding more computations to do for the GPU. And turns out this splitting and merging steps account for over 40% of the execution time in the entities. One recent effort, this is the only effort that looks into modifying the GPU architecture itself to accelerate the FHE workloads. What they do is they make all scalar cores support int64 and add a modular reduction step in all of them. They double the shared memory size in each SM and then have included a on-chip network where each SM can access data that is stored in adjacent SM's shared memory, and in a block scheduler that is fully able to exploit their on-chip network. And with these proposals, they argue that they see an 8 to 12 times improvement on standard benchmarks. But the issue with this is, with all these extensions, the GPU size increases by 26.6%. This is so big that it is not possible to fabricate at all, because the biggest chip that you can make right now is 858 millimeters square. Now, I will talk about our work FHECore and how our modifications to the GPU accelerate FHE workloads. So our architectural baseline is the A100 GPU. So you have your main memory, you have a shared L2 cache, you have an L2 cache which is shared among the multiple streaming multiprocessors. Within each streaming multiprocessors, you have an L1 cache, load store units on a register file. And we introduce the FHE cores alongside the other compute cores such as tensor core and CUDA cores. In the A100 GPU, there are four tensor cores per SM, and we mirrored this choice and saying that we will also include four FHE cores per SM. The reason to do this has to do with programming, and I can talk about that towards the end. With this decision, now we have 432 FHE cores inside the A100 GPU. Another key decision is that we multiplex the register ports access to the tensor core and FHECore. Before I say why we do this, it is maybe I'll share a few details on how the register file itself is implemented in the GPU. The register file has multiple ports to allow for concurrent execution of CUDA cores and other functional units like tensor cores. And now, since you are working, you would be working on the FHECore only in encrypted domain. You aren't really using the tensor core, so it makes sense to reuse the same port for tensor core and FHECore instead of adding a separate port to the register file. This also allows for reuse of the entire memory subsystem that is in the GPU, such as asynchronous data transfers or future memory optimizations like the distributed shared memory through the on-chip network in the recent NVIDIA GPUs. And this is the full microarchitecture of the FHECore. The FHECore is essentially viewed as a grid of processing elements, and each processing element takes 2 operands as its input. performs their multiplication, does a modular reduction, and accumulates it in an internal register. While writing the RTL for the functional unit, what we realized is we first wrote the entire Barrett reduction circuit as a combinational circuit and pipelined it until we could make the operating frequency of the processing element exceed the exceed the maximum operating frequency of the GPU. So in a systolic array, there are two ways in which you can perform the matrix multiplication. One way is to program one of the operand matrices into the processing elements of the systolic array and stream the other matrix from one end. This would stream out the product matrix. This would eventually stream out the product matrix. The issue with this is since the internal latency of the partial products that are traversing vertically is 6 cycles, you are effectively introducing a 6-cycle delay in every row of the systolic array. And this causes matrix multiplication multiplication between matrices of this dimension to be done in 116 cycles. An alternate approach to do the same matrix multiplication is to stream both the operand matrices into the systolic array and accumulate the product matrix internally in the systolic array. Now, since you can forward both the operands vertically and horizontally after a single cycle, you are able to perform the entire matrix multiplication in just 44 cycles. As for programmability, so we reuse the programming framework that is there for tensor cores as it is for FHE cores. The beach sections are for data transfers to specific registers in the register file. We take them as it is and introduce a new intrinsic FHE sync that does the modulo matrix multiplication and takes 2 additional arguments, mu and q, that are required for the Barrett reduction. This is compiled into the PTX version. From going from CUDA to PTX can be done through the inline assembly that is offered by the CUDA programming framework. But however, going from PTX to SAS is not as direct because the compiler backend of NVCC is not open source. So the way we handle this is we programmed FHECore as if we programmed the FHECore and wrote code as if it were the tensor core and compiled it to the machine ISA and replaced all of the IMMA instructions with our custom FHEC instruction. So this FHEC instruction essentially does the modulo matrix multiplication. In VU, you can think of it as consolidating a series of expressions that were previously required to do Barrett reduction into a single instruction. And this leads to a strong reduction in the program size. So previously, when you had without FHECore, you had a series of predication, additions, and multiplication machine instructions to be done to perform the modular reduction for all elements of the polynomial. Now, since all of it is being taken care of by a single instruction, there is going to be a reduction of the program size, and we see a highest reduction of up to 2.7x. And since we are accelerating workloads, our improvement in performance is going to be, and we see an improvement of performance also. Interesting note here for performance improvement is that we see a greater improvement in performance for the larger workloads compared to the smaller workloads like ciphertext multiplication, rotation, rescaling. The reason for this is the port sharing decision that we made. Because you are able to use the FHECore and CUDA core simultaneously, the warp scheduler is able to assign tasks to both of them in parallel. And yeah, so this is like a second order compounding effect that we see and giving us a boost in our performance. That said, we had used the A100 GPU as our baseline with 432 FHE cores integrated into the A100 GPU. Our area comes to 845.9 millimeters square, which is less than the reticle limit 858 and only a 2.4% overhead on the original GPU. Whereas the previous work, GME had extended a GPU that was 700 millimeters square to 886, giving it a 26.6% overhead. Yeah, so this was a collaborative effort with students and professors from BU, University of Murcia, University of Glasgow, and Northeastern, and KAIST. And yeah, I can take questions if there are any, but here's an interesting plot. Most of this work was done in the summer. So at the end of the summer, what I had done was we plotted the compute usage that was used on SEC. And we noticed that towards the end of summer, we saw over 100 times more usage than we were when we initially had started the project. So that was something interesting to note. Yeah. Are there any questions? I had to rush through some parts. Okay. Yeah.
I have a quick question. You said you did your evaluation with respect to the A100 GPU.
Yeah.
Is that design actually open source? So
No.
you can actually do an evaluation, or how do you?
That's a good question. So I skipped out on how we did our evaluation. So the way we collect these machine instructions is through NVIDIA's tool called NVBit. It's a binary instrumentation tool. Every time an instruction gets executed on the streaming multiprocessor, it kind of makes a copy and stores it into a file.
Okay.
And then there are open source simulators that simulate those instructions. So what we did was we modified that simulator and added support for our custom instruction FHEC. And that kind of gave the
This is all the simulation.
yeah, this is a simulation-based result. Yeah, and that is the only thing you can do.
The simulation with realistic answers, because copying out bits for each instruction seems to completely thrash all the caches that you might ever have.
So in real world, that doesn't happen. So we don't.
Yeah, in real world, it doesn't happen.
Right.
So how do you know that what you observe in simulation is corresponding to real world?
I agree. So what the NVBit tool does is it doesn't copy it to the cache. It copies it to a separate to an off-chip memory. So it.
How do you get there?
I would.
Teleport.
How do you get data from the CPU to off-chip memory without touching the caches?
Okay, maybe I don't really know how NVBit did that, but yeah. But so at least in the architecture community, when the contribution is on the architecture end, it is standard practice to use the simulators. It isn't really feasible to fabricate the entire GPU.
There's many architecture papers that show stuff on Gen 5 that does not even remotely hold up in reality.
That's
I
yeah.
mean, that's not just architecture. That's
That's all simulation papers.
We're over time, so I guess if Lohit has more time to answer questions, feel free to approach him. Otherwise, thanks for joining.
Thank you.
Hope you
Yeah.
enjoy the pizza.